Hello, my name is Ryan Mary, and you're watching an e-presentation on supplying renewable energy for electric vehicles through rooftop solar in Minnesota. This presentation was made for a conservation geography class and uses GIS mapping to assess whether there are enough impervious surfaces in Minnesota to supply electric vehicles through solar power energy. In this presentation, I will describe the importance of this research, give you some background information, explain the research question, show you my methods, and then give you my results and my conclusion, as well as describe some future research for directions to go for studying in this area. I'd like to start this presentation by touching on the importance of renewable energy. As we can see from both the picture on the right and the map of the United States on the left, different forms of renewable energies are becoming extremely popular in the United States, and mostly to reduce carbon emissions and reduce other greenhouse gases. We can see that various states, including Minnesota, which this study covers, have invested quite a bit of money into generating wind energy, and large solar farms are appearing around the United States. Now that we've touched on the importance of renewable energy, it's a good time to look at how different renewable energy sources have different land use requirements for energy production. This study, titled Energy Sprawl or Energy Efficiency, Climate Policy Impacts on Natural Habitat for the United States of America by McDonald et al. In 2009, looks at the various land use intensities for different renewable resources. We can see from the graph on the right that to produce 1 terawatt hour per year, biodiesel from soy, for example, takes 894 kilometers squared of land, where wind to generate the same amount of power only needs 72.1 kilometers squared, and solar photovoltaic only needs 36.9 kilometers squared. So what we're seeing here is that different forms of renewable energy have different land use requirements, making some of them more feasible than others to power our energy needs. It is this land use requirement why some renewable energy sources are infeasible to use for our energy demands. This, for example, is why ethanol can't work to power our cars. Dr. David Mackay, an engineering professor from the University of Cambridge in England, did a back-of-the-envelope calculation and found that if one lane of cars is driving 60 miles per hour and those cars average 30 miles per gallon, you would need an 8-kilometer wide strip of biofuel plantation to power those cars, and that strip would need to be as long as the road that the cars would be traveling on. This means that for every lane of cars that you would need to add another 8 kilometers to the width of that plantation. And this is not feasible for all the number of roads, especially in the United States, which means we need to find another source of energy to power our vehicles. The infeasibility of ethanol to fuel our vehicle fleet brings us to the necessary switch to electric vehicles. This study, titled The Technology Path to Deep Greenhouse Gas Emission Cuts by 2050, The Pivotal Role of Electricity by Williams et al., investigates how California can reduce its carbon emissions by 80% below the 1990 level by the year 2050. Two major sources which relate to vehicle and vehicle fuel consumption I've outlined with red boxes on the graph from the study on the right. The first one of these is electricity decarbonization, which is taking the electricity that is produced and moving it from carbon sources, such as coal-fired power plants, to renewable sources, such as wind or solar panels. The other way that you can make deep greenhouse gas emission cuts is by electrification of vehicles, which is shown as the yellow portion of this graph. And the electrification of vehicles must include cars and your general transportation vehicles, as well as other things, but this generation of electricity for these electric vehicles must be clean in order to truly meet these emission reductions. But in order to power our electric vehicles, we must come up with some sort of energy source in order to do so. Which brings me to my research question. Is the impervious surface area in Minnesota adequate to supply solar energy for the conversion of vehicles from fossil fuel powered to electric? start this study, I needed to find the number of cars in Minnesota that would need to be switched to the electric vehicles. To do this, I used the United States Department of Transportation website as well as the United States Census Bureau and found that 135,399,945 passenger cars are registered in the U.S. And since the Minnesota population is 1.7% of the U.S., we can use this ratio to estimate the number of passenger cars in Minnesota, which I've estimated at 2,301,799 cars, which need to be switched to electric power. Now that we know how many cars we have, we can figure out how much power these cars are going to need. It's been found that the average electric vehicle consumes around 5,400 kilowatt hours per year, or 0.0054 gigawatt hours. So to power all of the electric cars in Minnesota, we're going to need around 12,430 gigawatt hours of additional energy, which is 259% of the current electricity production of the state of Minnesota. So we can see that this is going to be a great challenge. This map shows the Minnesota solar installation and gives us a rough estimate of how much solar energy is hitting the state every day. I use the estimate of 4.35 kilowatt hours per meter square per day to give a conservative average in order to conduct this study. We can use this average estimate of solar installation to find out how much land area would be required to power our electric vehicles using solar panels. At 20% efficiency, which is the efficiency rating for the SunPower brand solar panels, a solar panel can generate 0.87 gigawatt hours per square kilometer per day, or 335.8 gigawatt hours per square kilometer per year. This means to generate the power requirements for electric vehicles, it would take 37 square kilometers of land area. But because of the high latitude of Minnesota, as well as self-shading of solar panels and shading from other buildings or obstructing views, we should compensate for this by roughly doubling this area, just to be on the conservative side, giving us 74 square kilometers to power the switch to electric vehicles. My study area for this project was the state of Minnesota, and my justification for using impervious surfaces is we can see that large areas of our industrial and city areas are devoted to flat roofs or other impervious structures such as parking lots, which would make for excellent areas of solar panels due to their flat surface structure and general lack of obstructing surfaces around them. My data layers included layers from the U.S. Geological Survey, as well as layers from the Minnesota Geographic Data Clearinghouse to construct this map of impervious surfaces in Minnesota. After mapping the impervious surfaces of Minnesota and excluding roads from the study, which would be difficult to build solar panels on, we can see that a large-scale map is difficult to interpret the areas that are impervious surfaces. But by zooming in to the Twin Cities area, for example, we can see that many areas exist that are impervious. And we can find how many of these 30 meter by 30 meter squares exist so that we can discover the area of impervious surfaces in Minnesota and throughout the entire state that can be put into solar panels. From this, I concluded that there are 170 kilometers squared of impervious surfaces, excluding roads, that exist in Minnesota. And since we only needed 74 kilometers squared, we have enough area of impervious surfaces to power an electric vehicle fleet. In fact, 63% of the available impervious surfaces would need to be placed into solar production, meaning that we could be semi-selective in our areas as far as making sure that there are not other obstructions shading the solar panels, and that the construction costs would not be too great in certain areas. How can we install solar panels onto these impervious surfaces? You can see from the picture on the left that the University of St. Thomas in St. Paul, Minnesota, has installed solar panels on the roof of our student center to generate electricity. The picture on the right shows the Tiny Diner in Minneapolis, which has installed solar panels over top of their eating area. And this raised area would be easy to install over parking lots and other types of impervious surfaces. Future research in this study can look at powering national or global shifts to electric vehicles outside the state of Minnesota and whether impervious surfaces are large enough elsewhere in the country. It's also important to look at powering the electrification of public transportation and also powering larger population demands, so increasing the number of vehicles that would be in our fleet, as well as the impacts of the intermittency of solar production. For example, since solar cannot function at night, is there going to be issues as far as powering our electric vehicle fleet? Thank you for viewing my presentation. I hope you now see that the impervious surfaces of Minnesota are large enough to power electric vehicles through solar panel production.